So welcome you. We will start with lecture 3 and we are back from radar system theory back to wind turbines problem. So where is wind turbine problem? Wind turbines are usually located, of course, on coast, at sea, on hilltops, on the mountains ridge and so on, where is very good visibility. Unfortunately, what do you think, where is placed radar? Also need good visibility, so this coincidence, it is really serious and we need to take care about it. Wind turbines is great source of interference for our primary radar system or weather radar. It overlapping targets of interest of echoes and degrading radar sensor performance generally. And of course, if will influence like air traffic control radar, it could cause it really big trouble and a lot of casualties. So how degrading radar sensor performance? Usually by suppress due to adaptivity false detection, so-called constant false alarm rate. Because imagine, what is constant false alarm rate? It is some constant where is decision of radar, is it their target or is not their target. And if you will have big reflection from wind turbines, then this threshold will be extremely high because there is strong reflection. So it is clear that we need this adaptivity just suppress. Also braking tracks, what this mean? You have individual detections and you follow where is your target, and now in half of the way you are just disappear target, you don't see anything due to these wind turbines. So detection capability of PRS can be limited influence of VT by reflection of radar signals, it is major problem. Mirror reflection, it is minor problem and our model don't handle it with this because it is not so important. And EM wave diffraction, it is shadowing behind the wind turbines. We already make analysis on this and discover that some shadowing is present, but it is not so big, so also is not included in our models. You will see later that even our model is already enough complicated, so we don't use these two things. For the development of suitable mitigation techniques, you need, and it is really necessary, need a large amount of radar data under various wind turbine conditions. And this is problem, because you can't have it large amount of data under various conditions, because imagine it is like if you have access to wind turbine and around wind turbine is in a circle some road. Okay, then I can move it and measure from different angle, waiting for different speed of rotation, but it is not possible in radar environment, because it is in environment, because there is not this road. Usually when you see where wind turbines are located, there is not accessible road, so even you don't have permission go to this place and so on. So for this reason we develop this simulator that can help you and model everything. Of course, it is simplified model. This model don't follow reflection from environment, because it is not possible modeling. It is so computationally hard that this model will never work. Of course, somebody told me few months ago, you can use some ray tracing method. In 10 kilometers per square, ray tracing method? No, I think that not exists so powerful computer to do it something else. So we need simplification model. So, and this, all these things, why we can't, all this thing leads that all mitigation techniques, due to high variability, needs to be, all mitigation technique must be based on high adaptivity of these mitigation techniques. Because if you develop some mitigation technique for one wind turbine under one conditions, under other condition will not work. So, how looks received signal? How looks received signals in case that what is including or received signal to radar? You know that will be for sure some noise. Always noises everywhere. It will be ground or sea clutter. It is a reflection from environment. It will be weather echoes, so it is mean it is cloud also, and it will be real target. And plus, it will be close to wind turbines, will be reflection for wind turbines. And all these things and other things, you need to remove it before you make an exact detection of your target. And of course, you need to remove it in real time. You don't have time to make some analysis and so on. So, where you could make analysis of influence of wind turbines, you can imagine that you get reflected signals. So, how do you think that looks these signals in time domain? Like random signals, because it is summation of all reflection together and you get one time signals. Okay, complex signals, amplitude, phase and so on, but it looks like random. So definitely you can't make any analysis in time domain. Then you can make analysis is spectrum domain, and of course we use it mainly spectrum domain. But even, how we will see later, spectrum looks like also random variable. It is not random, I must say, in advance. We discovered that it's not random, but almost looks like random. So even just spectrum in specific time is not enough. So, and if you want to see evaluation how looks this influence in wind turbines, you need spectrogram, like is evaluation of spectrum in time. So it is best thing what we discover, what is best for this analysis. About spectrogram, I just want to mention one more thing. You probably know what is spectrogram. Spectrogram is this. So each cut in each specific time is spectrum. And now you will have problem. You already know that from previous lecture that the Doppler resolution is maximum Doppler frequency depends on PRF, pulse repetition frequency. And imagine that your maximum pulse repetition frequency is some value and maximum Doppler will be, like example, plus minus 500 Hertz. And now imagine that your rotation of wind turbines will be so high at end of the tip of blades that produce Doppler that will be 700. So what has happened in your spectrum or spectrogram? Aliasing. And it is another problem. Then you discover that you will design mitigation technique, everything, and now you want to apply to real system and discover that your algorithm stop work. Why? Because aliasing occur due to this high speed. And how you can influence? Increase PRF. But very often radar is somehow designed. It is already in an environment. You can't just change it some this input values. So this is also another problem. So there on this next two slides will be a list of negative influence. So increasing size of wind turbines, large blades and structure, of course tower also, because tower is like static object and it is caused reflection, yields to higher radar cross section, more higher radar cross section. And you can see that we previously compute example when we radar cross section of target was about 2 meters square, and reflection from wind turbine RCS could be from 110 meter squares up to 1000. And it is depends on rotation, what is yield and what is the angle between PRS and so on and so on. So it is really complicated. Next problem is growing number of wind turbines. Of course, more wind turbines, more problem. Is it clear? I think. Intensive spatial expansion, because now we don't have only onshore wind turbines, but also offshore, close to coast. And where you want to see on coast, coming some plane, and it is really big area where should your radar be blind. Then we have wind farms. It is the worst scenario, these big wind farms. I will show you yesterday this Tamil Nadu area where was wind turbine every 300-400 meters for radar. This must be really terrible. Large RCS blinding radar. So it is not mean that radar not see what is there, but he see also only big target. There is big target, big red point, large point through not only one resolution cell, but through many of them. And it is not important if it's passed through this area some target or not, because you don't see. There is some stationary target from wind turbine reflection. Then identification of speed of this target is also really influenced by Doppler shift of rotating blades, because how I told you, at the end tip of the blade, the speed could be from 800 up to 1000 meter per second. But it is speed of planes. It is similar, if you can imagine. And the speed of blades is variable. It is depends on blade length and rotation speed. So this speed of at the end of tip could vary from 100 meters per second up to 1000. It is so big variability that is really big problem. Also, variable rotation. Imagine your radar looks by this, and you have all this rotation, and in every rotation will be another cross section. How you want to design and some mitigation and wide range of rotation speed, because old one they have relatively quick rotation speed up to 15 RPM. Now these long blades, modern wind turbine, they have speed 6 up to 8. Due to longer blade, they could have lower speed. So variability of speed could be from up to 2 RPM until 15. Like example, something like this. But this depends also on the size of wind turbines. Next is variability in the turbine dimension. Of course, if I have 20 meters high tower or 100 meter or 150, it is also different. Different blade design, shape, number of blades, materials, everything this influence your radar cross section. Multipath and clutter effect, because imagine that if you have multiple wind turbines, the signal is not go just to wind turbines and back, but it is reflected to another wind turbine and back, another wind turbine. So it is multipath effect. It is also a huge problem. Also can cause it shadowing and blocking, of course, it is clear, so you don't see what is behind the wind turbine. Frequency dependency. Imagine that you design some mitigation algorithm, everything works perfectly, we are in ideal world, but it will work only on some carrier frequency, in another carrier frequency will not work. And cumulative interference in wind farms, I already told you. So you can see all these things together. This looks like almost a random process, if you agree with me. It is so many different variables. So there I get from internet one very interesting presentation. It is from company Raytheon. It is American company that developing radars, very well known. It is US company. There you have link where you can download this PDF. It is from some conference, and check. They make analysis of two areas. The blue spots, it is reflection of wind turbines, and they combine with radar where is not any wind turbines, just for checking what is their influence. And check this is track. Green, it is mean it is good. I see target, I know where is target, everything. And check the red one. Red one means I don't see target, I don't know where is it. Of course, how they know where is it? Because they have some GPS or something, it is testing scenario. But maybe 40% of track is just disappear. And imagine that will be some target that you need to know where is it. It is not good. There is different free plots because it is different heights, so 4K feet, 6K feet and 8K feet. Of course, if you are higher, it is better. Is it clear? But imagine that you have some wind turbines close to airport when you are landing. It is almost not possible. This is another example. This is wind farms cause false air traffic. The air traffic system means that this is target, that is planes. Yeah, but it is not planes. This is showing example what's do it radar clutter. There is no any clouds on weather clutter, nothing. It is wind turbines. But it is also problem. Imagine that you send information about to planes. Okay, there is storms, you can't use this airport, you need to go to another place. No, it is wind turbines. Of course, always somebody told me, okay, so I will tell them there is wind turbines and be careful. You can ignore these results because wind turbines are static, they are not moving anywhere. But it is big area. You can't lose information about this so big area, information about this. And this is also can cause it in weather radar false clouds. It is looks like clouds, wind turbine. So there is really nice examples of different influences of wind turbines. And check this one. Another example, the green one is good detection and the red one is bad detections, lost detections. 50% in average where radar loss detection, but this is terrible. And why? Look at the location. Of course, wind turbines are on the top hill, where they should be, of course, where is good wind. I understand developers, but from radar system point of view, it is almost the worst scenario. Okay, now we move to wind turbine components. We have two main types, horizontal axis wind turbines and vertical axis. The second one, vertical, we don't consider because honestly I don't see these wind turbines in my life with vertical axis. It looks like strange shape. I don't know, do you have experience? Do you see it, this vertical axis wind turbine somewhere? I know that exists some experimental setup, but 99% will be horizontal, so of course we don't consider this vertical. And what is base wind turbines component? Foundation, okay, we don't care, it is underground. Tower, we care. It is for a static object, but this static object is relatively easy suppress. MTI filtration, moving target detector indicator. So it is clear that this is not moving and it is static. Okay, it causes a problem, but I can easily find a solution. Tower, Okay, it is tower. Nacelle, it is this one. It is not so good because it is big object. I know that it's not so quickly rotating because it is slow movement. It is depends on wind direction, but still causes some problems. But still, it is quasi-static because if you imagine that we send PRI every microseconds, the movement of due to changing direction wind will be almost zero with comparison with this speed. Then we have hub and blades, it is clear. Unfortunately, blades is also very complicated shape. It is you probably saw it. I can't describe it in English, but it is very complicated shape. And imagine when your signals come, the reflection will be totally different. And it is also very, very, very hard to modeling. Because if you want model RCS really precisely, you need to take complete model of blade and use it electromagnetic wave that will compute by exactly solving solution this RCS. Good luck on 10 gigahertz. Do you know how many scatters will be? It will be millions and millions. And you need for the whole rotation, and a rotation could take 6, 8, 15 seconds. It is not almost possible to solve. You can solve for one blade theoretically in CST studio or something like this, but not in movement and so on. So this is possible approach, but not easy. So there is typical parameters. Number blades, 3, of course. It could be 4, 5 more, but honestly I never saw it. I always see only 3. So our simulator can adopt it, so you can choose any number of blades, but we always simulate it only 3 because it is majority. Then is height of tower. It could be from 40 meters to 260 meters. Length of blade from 30 meters to 100. It is typical parameters. Of course, that exists some blade that could have blade length 1 meter, really small one, why not? But we consider some typical values. Rotation speed, how I already say, from 5 to 20, typical, normally from 2 up to 20, something like this. Initial angle, where is start rotation. It is important because where you start, then from this position you know where is position each blade, and it could be any. It is a random variable. But how you will see, it is not for us important. I will describe later. And power of wind turbines, and it is vary. It is from, I don't know, half megawatts until 10 megawatts, 6, 8 megawatts, something like this. And blade tip, the movement at the end of blade tip is at maximal wind is subsonic. It will be about 1000 meter per second. So it could be sometimes even faster than wind speed. So this is really, really big problem. Okay, do you have? Now I will present you wind turbine size. We have different type of categories: small and micro wind, medium, modern utility scale, onshore and offshore. So if you can check small and micro wind turbines, it is like this. It is really pico or a really small one. Maybe you will make fun. Why I consider this? Imagine you have radar system that detected UAV. It is same size. So it is not, I know that looks like fun, this homemade or something, but it could cause it even this small problems because it is same size UAV. And imagine if rotation speed will be of this small one 40, 50, 60 RPM because it is short and very quick, it could cause also problem. Small 1.32 meters and rated power I will not read, hub height 6 to 12, residential 3.6, community, and so on. So it is this smallest one for home and so on and so on. Maybe you know this also, this small one in when you have how to say in Wild West, when you have some these turbines from it is same, and they have it about 10, 12, 14 blades from Wild West, from movies, and this one. So but it is also problem. It is again UAV. So reflection will be also big. And I discussed this with one person from radar company, and he told me that that even this one really can cause it RCS relatively big, that radar see this wind turbines. I almost don't believe, but it is true. Then we have medium and scale wind turbines. It is for agriculture campus and some older commercials. It is from 20 to 40, 40 to 60. It is not big one. It is older one, how I say, from 90s to 2000, when it was evaluation and starting development. How you can say even in your country start about 1990, so it is like example, good example. Then we have some modern, it is like from present time, and there I have even model examples. Vestas, Siemens, GE, another Vestas. This is relatively modern and now is used from 2020s very often. We have a lot of them even in Czech Republic, maybe even you have it there. It is like rotor has 150 meters. Blades about, it is rotor and blades about 166 meters. So you can see this is to be fun. It is really large fun. And imagine this. In this area, radar is completely blind, completely. And then we have, I think that in present time, about 2020, 2023, it is the biggest one what is installed. And of course, with increasing future, it will be larger and larger. And is it clear that if they have larger blade, they have smaller rotation speed, because if they will have same speed, tip blade speed, it will be maybe more than 2000 meters per second, something like this, because it will be really huge. Then we have offshore wind, and they are bigger. Why? Because nobody cares. It is close to coast, it is undersea, and there is a lot of space, how you can see. I saw some picture close to Britain in south part, and there is some wind farm. There is hundreds of them. It is really huge wind farm. And the largest one, Vestas, it is about 236 meters with hub blade 170 meters. Imagine installation of this. It is amazing. It is great technology, honestly. So, and it is latest generation. Maybe exists some new one, but I don't know them. It is the last one what I already found. So, there is how wind turbine works. It could work synchronously, like directly grid coupled and invert based. If will be synchronous, it is mean that they operate at relatively fixed rotational speed tied to the grid frequency. So it will be constant. If something is constant, it is easier to mitigate. Why? Because it will be still similar, how to say, properties of this, because it is constant. But unfortunately, modern wind turbines are inverter based, and since both blade rotation and inverter harmonics contribute to the clutter spectrum, and they are not synchronous, so it is caused problem, because this will be hard to predict and hard to mitigate, because it is not synchronized. And unfortunately, this is modern version. Okay, now I will show you some wind turbine mitigation approaches. First mitigation approach is turbine side mitigation. So it exists some special material that you will use and cover blades, and reflection will be almost zero. You know for sure stealth target, stealth airplane. It is same. One problem, extremely expensive. Extremely expensive. Second problem, the stealth material is not for a long time. You need to repaint it, you need to recover, and so on. But of course, for radar specialists is good. It is mitigation technique on side of wind turbines. But can you imagine that will some developer if wind turbines you will pay for this paint? No. So unfortunately, it is not, how to say, it is nice solution, but I think that nobody uses it almost, because it, and especially from reason is price, it is really expensive. From radar side, there you can see it is plenty and plenty of different solutions. First is infill gap filter radars. So in area where you have wind turbines or wind turbine farm, it is better, you will place additional radar that will cover this area. But what do you think? It is good solution relatively, but you need to buy new hardware, and it is extremely expensive. Again, we are back. Always we are back at money. So it's really expensive. Then we can make it antenna diagram shaping. So it is mean you see antenna diagram. It is something like this. Main lobe and so on and so on. And you will plan your antenna diagram in the way that wind turbine will be always in this 0 point. So it is mean there not will be any reflection. It is hard technique. And of course, imagine with rotation speed, or imagine with radars that is not stationary, but you can move them. You always need recompute. So it is good solution, hard to implement. Then is adaptive limitation of side lobes. It is whitening and so on and so on. I will show you later. 3D or waveform strategies, and it is about pulse waveform. You will use so complex waveform that you are sending that they pass through this limitation. You changing waveforms of radar that transmitted pulse, and from comparison of results you could mitigate. But it is very, very complex, and it is not easy implementation. It is mean you can't say, okay, so we will design one time and then we will use it everywhere. No, you need always adapt to specific place, specific parameters, specific implementation. So it is hard. Wind farm sittings or layout optimization, it is mean more organization thing from national point of view, like from government point of view. You told developers in this area you will not make wind turbines because it is close to airport or something like this. But it is good solution. But for present already installed wind turbines and radars, you can't do it anything else. But it is not bad solution, honestly. I like it, this one. It is only about careful planning. But problem is that sometimes where should be wind turbines, should be airport also. And then operational procedural mitigation. It is more about NOTAMs or ATC, air traffic control, that told you in this area, just don't go to this area, just fly around because we can't see you. Okay, it is solution, but not permanent solution. It is just temporary solution. And then is signal processing approaches. Only signal processing. And of course, we develop one technique for validation of our simulator that is based only on signal processing. And we already published paper about these techniques. And signal processing approaches are unknown because every radar developer told you, okay, we have some techniques, how do it? Nobody told you how, because it is really big know-how how they do it. So publicly is almost unknown. I know only our solution because we develop and is publicly available. What is big advantage of this signal processing approaches? You don't need change hardware. It is just software. So you will update software, something like this. So it is our primary focus on this one. Okay, so and now we'll go slide by slide about one turbine side mitigation. So first we start with this material. It is radar absorbing materials, so RAM, radar absorbing materials in blades and tower. They have steel shaping and coating scatter radar waves, so it is not mean that they attenuate wave, but the scatter wave outside where radar don't detect this signal, so you don't care that go outside. And this is same principle in stealth airplane. Yeah, because you know how looks stealth plane. It is always so different shapes. And why do you think these strange angles? Because reflection goes out and not go back to radar. So it is hardly detectable. It is only about this. Plus this material, of course, not only shape, plus materials. This reduce in very nicely about, I read some report again from Britain, and they make some analysis that reduction of RCS is 99%. It is nice, really good solution, but expensive and limited. And of course, imagine that if you want to do it for already wind turbine that already stay, you need unmounted, unmounted everything, covered by pane and just mounted back. So it is not possible. It is clear. So it is turbine side mitigation technique. Then we have infill radar or gap filler. So it is mean that there is wind turbines, there is original radar, and you can see this is area and this is problematic space. If you don't see there, then you put another radar infill that will cover from another angle this space and send information like to original radar or to ATC or something like this. But it is expensive. You need to buy another radar. It is special kind of radar, just infill radar, and it is just for covering some special small areas where is wind turbines or some other source of clutter, of course. It not could be only for wind turbines. It is costly, and it also requires terrain and spectrum coordination. Why? Because you place new radar, so new transmission, new permissions, everything new. And look, there is example of installation of this. It is infill radar, and there is one and second, and it covers from both sides this wind farm, and you can saw it. But expensive. It is exactly two radars. Antenna diagram shaping. It is shape of radiation pattern of the radar for reduction impact of turbines in specific direction. So in direction where is wind turbine, you will shape antenna design diagram that there will be zero. So then there is no reflection because there is no reflectivity in this direction because antenna shape is zero. So it is adjusting antenna radiation pattern, but adjusting antenna radiation pattern is not an easy task. It is tightened with already designed antenna. So how you want to do it? If you have some antenna, you need to prepare new antenna. Or if you have AESA antenna, then it's possible, because this is more software solution how you shaping this antenna beam, but still relatively complicated. And what is problem also? Okay, in specific direction you don't see wind turbines due to fact that there in antenna beam is 0. Okay, you don't see antenna, but in this direction you don't see even target because there is 0. Okay, you mitigate wind turbines, but in case that in this direction will come to you target, there is 0. You don't see even target. So mitigates clutter, but no news radar required. It is pros, but negative is creates blind spot in nulled sectors and needs complex hardware calibration. It is not easy task, because of course if you have one wind turbines, relatively easy, you need one null. But if will be 200 of them, 20 of them, it not will be almost possible. Then is adaptive limitation of side lobes. It is side lobe control techniques which aim to prevent wind turbine clutter from entering the radar through antenna side lobes rather than the main beam. Then we have classic side lobe blanking. It is SLB, side lobe blanking. And then we have side lobe suppression. It is SLC technique. And then we have side lobe cancelling technique. And then last one is whitening technique. So it is all similar techniques that like based on side lobe operation. Advantages of this one is establish techniques that can be retrofit because it is well-known techniques. It helps reduce false alarm from off-axis clutter, and they do not address clutter in the main beam. So it is good one. One SLC technique, very interesting, is patented by Intersoft patent. You can just open later this patent and check it. And nobody can use it now because it is patented, but I think that expiration is until next 5 years or something like this. Then will be publicly available because expiration of patent. I think that I check it 5 years, something like this. So you can check it later. And what is negative? May not address main lobe reflection. Effectiveness highly is geometry independent because it is side lobe. Of course, all you play with is antenna diagram, and can attenuate legitimate targets. Why? Because you play with side lobes, you limitate side lobes, and if you will have target in these side lobes, you will mitigate also. And it is another problem. Any mitigation technique, if target will be close to this wind turbines, you don't mitigate only this wind turbine, you will mitigate also this target. So you need to be careful on this, especially with this null technique and all this. Okay, I can say, okay, don't watch there. But if target will be there, then you have problem. Then is pure signal processing approaches. First one is STEP, space-time adaptive processing. It is very promising method. It is adaptive filtration based on multiple transmitted pulses and multi-beams concept. It is really modern method, but I must say it is very high computational load. It is very complex and hard to design. But I think that is also one of the future of mitigation technique. It is good one, but it is very hard to design. But what we'll see maybe in next 5 years is not will be so hard. It will be maybe some new optimization technique and will be easier. But it is good one. GMAP for weather radar clutter suppression. Then microdoppler signature classification. Okay, you know what is Doppler signature. If I have moving target and my signal reflected frequency will be different due to movement. But what is microdoppler? You know helicopter for sure. And imagine you have helicopter and helicopter has blades. Do you agree? So the movement causes Doppler shift. So it will be Doppler shift as you know. And what is microdoppler? Microdoppler is Doppler shift of this wind turbine. So there is like two different Doppler shift. Doppler shift from movement and Doppler and microdoppler. And why we call it microdoppler? Because this Doppler is relatively small with comparison of Doppler shift of plane, because of course it is high speed. So how you can recognize, okay, Doppler causes that your central frequency will be moved. And microdoppler means that it will change like slightly spectrum of, like it will be like jittering. And this jittering you can identify, and it is special for wind turbines. And then if I can identify, I can play with it, I can mitigate and so on. So this is microdoppler. Microdoppler, you can have it also in UAV. UAV, motion, the frequency is shifting, but you have 4 blades, like quadrocopter, you have 4 blades. And this causes this microdoppler shifts. So it is small changes in Doppler shift. It is like sawtooth, like that will be changing something like this. And what is interesting, this microdoppler is hardly to identify. Why do you think? You need really big resolution in Doppler, because it is so small shift. So you need to have a really good resolution in Doppler. But if you are able to identify, then this information even you can use for classification of target. And I saw some presentation of radar system on very short distance, like 5 kilometers or something like this, 10 kilometers, that is used for protection like nuclear power plant or some important object, and they can detect this, how to say, UAV, and even told you, okay, from this it is quadrocopter, it is this one, it is this one. And usually it is based on microdoppler signature, because each UAV will have specific signature. It is like signature, like your, exactly, or like our fingerprint. So it is like exactly, yeah, fingerprint of for this UAV. And wind turbine is something similar, if you think. This causes Doppler shift or microdoppler. It is depends how you call it. Doppler and microdoppler. Microdoppler means it is only small one, but it is also Doppler shift. What is advantage? Best advantage, no hardware upgrades. It is good one. Oh, okay, maybe some computer resources for additional software, but it is still okay. It could be adaptive and flexible. Why? It is software. I can just reconfigure. It is software, so it is easy to adopt. Quick development, relatively. Why? Because if not fit to my area, but fit to another area, I will adopt it. It is software, and any software can be relatively easy adopted, so it is okay. What is negatives? High computation load. It is highly computation. You need really good computer, powerful resources for computation of this, but still it is possible. Then requires careful tuning, and this is hard, because it is like there is not any rules how you can find pure solution, because you need to tweak and founding and tweaking parameters to get the best solution for you. And sometimes small changes of one parameter cause completely different result. So it is not easy because it depends on many variables. So it is not mean that you found some solution, partial solution, okay, and now I will tweak very easily. No, because even small change cause big changes in this mitigation technique. So it is not easy task, but relatively possible task. And you just need software and programming skills, so it is good one. So I will tell you something about our solution. Our solution is based on DSC based approach. And what is DSC? It is dominant spectral component, and from now you will see this shortcut DSC 1000 times because dominant spectral components, what could be, you know that how will looks probably spectrum from wind turbines. It will be some very complicated spectrum due to different angles, different RCS and so on from different direction. But where will be worse Doppler shift? At the end of the blade. Where is tip speed the biggest one? Do you agree? And this blade is shifted about 120 degree. Do you agree? Because we have 3 blades, so 120 degree. So the worst amplitude in spectrum will be from tip end of one blade, second blade, and third blade. So our approach is how detect this 3 worst component, how estimate where will be in future, and mitigate. And for this we use Kalman filtration. Do you know Kalman filter? If you heard about it, I don't ask if you know complete algorithm, but you know about Kalman filtration. Mr. Kalman, it is a professor from Hungary, and I think that he died before 5 years. It is relatively new Kalman filtration. You will see, I have some slide, discovered this type of adaptive filter in 1965, 70, something like this. You will see later. So generally our approach is that we found these 3 worst harmonic components. It is mean with highest Doppler shift. We will try investigate where will be in a next sample, where will be their position, and then we design filter and mitigate just these 3 points. And you can say me, okay, what the rest? Rest is remaining, but rest is much lower reflection that end of the blades. So okay, we make reduction, not 100%, but maybe 80%, 70%, but still better than nothing. If you get my point. So
trying to draw a circle with these 3 points, like trying to draw a circle with these 3 points.
Yeah. But it not will be so easy how you will see, unfortunately, because we are working in spectrum. So you have 3, okay, I will show you 2 lines, but it's 3 lines. That constantly, because it is Doppler shift, they do it, but not regularly, and they are free. So when you do it this one, you don't know that this was first and this was second, and they are free, if you understand. Okay, this is one, and check. I will do it this one, after you don't know what is first one, second one. Plus, we have aliasing. So this goes there, and now comes from there due to aliasing. So it is almost looks like a random movement. So it is not easy. You can't say, okay, it is in, yeah, you are right, it is in circle, completely agree, but in spectrum it's not so like this. Next approach is for 3D radars or HPRF, is high pulse repetition frequency, and waveform strategies. It is used only for 3D radars which know range, azimuth and elevation with multi-beam. And I can design some adoption algorithm, and I have multi-beam. So one beam of antenna look at this area, this area, and from comparison of the results I can design algorithm and mitigate somehow this one. But I need good resolution in Doppler, so it is mean high PRF. It is improved Doppler and high separation of clutter and targets, because you will detect these targets by multiple beams, so you can then easily separate it. But I say easily, it is not means it is easy. I can separate it, but it is relatively hard. And I must say that public solution, I don't much saw it. I heard about always somebody tells something, yeah, this exists, but nobody gives you details, because again it is big know-how. It is good for excellent clutter separation, improves multi-target tracking, negative high cost and long deployment and complexity. It is not, again, tightened with geographic position variable radar. You designing this just for like one solution for one radar for this area will works. It is not mean that is universal general solution. And with long deployment and complexity, of course, high cost, because you need to really have specialists about this one. And long-term evolution plan, because you will not develop these methods in 1 to 3 months. It will take not years, but long time. But it is promising strategy, this one. But not easy, because it is combination lot of things which you already know, of course. Waveform strategy, we know different waveform, we know what is this, we know how works 3D radar. So it is just all combination put together, but this is so many variables that is hard. Then is wind farm sitting, layout optimization, optimize turbine placement to avoid radar line of sight, leave corridors open to radar, use terrain as shielding, it is good one. Requires early regulator involvement. It is for future development of turbine, it is good and relatively easy. So, okay, how to say? It is good for radar system engineers. It is not good for developers of wind turbines, because they forbidden you. No, there you can, because there we have corridor. But you get my point. It is cost effective if planned early, reduce need for technical retrofits, it is good. Negatives, not applicable for existing farms. It is main problem. And developer constraints may apply, of course. This design farm require a holistic strategy, and I don't think that this happened. In present time it is improving, but not in previous time, because usually nobody asks radar specialist, is it involved, this one, because nobody knows that there is this possibility. But now it start improving. I know that in Czech Republic you need have permission if it close to radar. Okay, how will influence, if influence forget about wind turbines or something like this. But it is more about government problematic. Then operational procedural mitigation, sector blanking. Okay, if like I have only one wind turbine which affect me only one resolution cell, what is most easy solution? Okay, in this one resolution cell I will just make blank, there is nothing. Okay, I lost information from this one cell, but it is not so big loss, if you understand me. I will just suppress and tell, okay, in this specific cell, stop looking, don't show me target, ignore. ignore, it is best word, ignore. Or another could be define transporter mandatory zones. It is mean where planes could movement. So it is mean you will avoid place movement around wind turbines. But sometimes it's possible, sometimes it's not possible. Again, we are back. If it will be somewhere close to airport, you don't have this possibility. Adjust ATC procedures. What is mean this one? Adjusting like minimal controlled flight zone. If not, will be 300 meters. If will minimize flight zone will be like 500 meters. Okay, we are up. Is it possible? But imagine if you will apply this globally, everybody must accept it. So it is also not easy. And publish NOTAMs. And NOTAMs is like messages from individual airports which protect some area and told you don't go to this, go to this way. But it is not permanent solution. It is just solution, okay, I won't saw it them, so I told you don't go there. And make over. Okay, there will be a list of companies that I put to my list, which I found that develop some solution for wind turbines. Generally, almost all of them, they are just hardware solution. First will be Therma. They develop Scanter 4002 radar. It is this one. And it is typical example of infill radar. So you will place these radars close to wind farm. And this radar saw it in this area where it's wind farm. But you need buy this one. It is 2D primary radar in X-band. How you can see, range is from 80 up to 100 nautical mile. It is about 200 kilometers with resolution about azimuth resolution is under 1 degree. So it is really nice resolution. All this information, of course, I get just from website. I don't have access to this radar, so from data sheet and so on. So please don't ask me for any details because I am not customer, so I don't know these details. It is optimized for airspace surveillance and gap filter roles. So it is just additional classic radar. But some smaller one, so not classic big one, but still it is radar. It is wind farm tolerant. They have application of some special signal processing technique also. I don't know which one, nobody tell you. With strong clutter suppression algorithms. Exactly, algorithms. We can guessing. It is based on compact solid state transmitter with high MTBF and low slide cost, and it is deployed in UK in around wind farms. More information, unfortunately, I didn't found it. Because of course all radar companies are relatively careful. They always relay some data sheet, but only base information. If you need to detail, you need to ask them, and if you will be customers and you want to buy, they will tell you. But if you just want to know from academic reason, they didn't answer you probably. Second is Throughput company. They have product, call it Midas Free, and ACMS and DSMS, and it is analog clutter mitigation system and digital clutter mitigation system. So it is for analog and digital form, but it is similar. One is analog, one is digital. And check, it is not radar, it is just mitigation system. It is widely distributed small onshore wind farms under the coverage of analog radar or digital, and solution is in the video domain. This algorithm is based on how to say, on some high-speed logic processing FPGA algorithms. I don't know details. But this is devices which you connect something between radar and visualization, make probably some setting, and this clutter from wind turbine is removed. So it is like, it is not bad solution because you don't need a new radar, but I don't know how it works in principle. Based on transition and clutter zone using color detection, but it is just general description. So, but it is a nice solution, I think. It is not bad. Then is Thales. It is one of the biggest radar companies in the world, Thales. They have Star NG and Trace NG. It is again primary radar system. This one is, I think, Star NG is 2D radar and Trace is 3D radar. It is from 60 to 200 nautical mile with good azimuth, and elevation, of course, is not covered in 2D. This radar looks like this one, this installation. And this, what I already only found, that have some special wind farm filter integrated into digital processing chain. So it will be just algorithm. So maybe this will be partially only software solution. But again, you can't find any other information. This radar use solid state transmitters, again MTI, MTD filtration, and designed for approach and route ATC with continuous updates, modular upgrades, high availability. It is like from classic datasheet. So more information is not possible to find it. Another one is Availlant. Again, it is some part of Thales. It is holographic radar in 3D continuous wave holographic radar, and it is CV radar, continuous wave. So it not works in pulse regime like send pulse, wait for answer, but it is continuous wave. It's continuously transmitting, like never ending, still continuously transmitting. But it is completely another principle, and we focus only on primary. So provides continuous 3D picture. So it is 3D, so you know azimuth, elevation, range. It is in 3D picture and don't have any mechanical rotation. So it is very, very, very interesting, this radar, and looks like this one. And this radar can separate turbines vs aircraft using some unique signature. And I have suspicion that will be this micro-Doppler signature. But I don't know, I am guessing, of course. I don't have more information. And it could be used like classic infill radar, only not 2D like in preview case, but in 3D. It is interesting solution. Next one is Hensoldt. I think that is Dutch company. It is Hensoldt ASR NG. NG, I suppose this is new generation. It is very now popular name. And it is 3D radar with integrated secondary radar. So it is primary radar plus secondary radar. And you can see it is very similar to radar that you have in Guwahati from Eldis company. This will be primary antenna of primary radar, and this will be secondary. Antennas looks always almost similar. It is for a reason, because it is from principle what you want to do. So you can see, and this black one, if you can see 1, 2, 3. It is mean that there is 3 different regime, because it is like shaping beam that's sending energy that is reflected to area and received back. So sending energy is by this free beam shaper or something, how to say, reflect and travel back. And why SSR don't have these illuminators? Because SSR is secondary surveillance radar, and secondary radar only receive information from planes where is this devices that just send information. Where are you? And check answer back. So there is no reflection. It is just listening time. So for this reason, there is not illumination. It is multi-beam 3D processing. Exactly, multi-beam. You can see this free and integration. By the way, I always told you that secondary radar asking, okay, where are you, and send back. There is 1000 more information. It is not only about this. It is about altitude. It is about. There is even some special codes. If will be planes hijack it, then somebody just press button, and this device send some special code. We have problem, and so on and so on. There is a lot of information. You can send, I think, 1200 bytes or something like this. So there is a lot of different cells. It is a relatively complicated protocol, but generally for simplification like this. Then we have Indra. Indra, it is again 3D radar. And 2D, 3D and 2D radar, solid state, azimuth resolution 0.5 up to 1 degree, elevation available in 3D variant, what is K features, advanced MTI and CFAR algorithm. So it is tailored for clutter environments. So it is mean it is works also for wind turbines, because wind turbines is another type of clutter. It is flexible architecture for S-band for approach and L-band for en-route. Inherent wind farm mitigation due to use multiple pencil beams. And you can see it is first representative of multiple beams. This 3D radar, it is this 3D HPRF techniques. And I already found that already working in UK and Spain. More information, sorry I don't have it. And then is Leonardo Electronics. Again, secondary, primary radar. There is special wind farm interference mitigation algorithms. And it is all what I found about this, nothing else. It is deployed in Europe and in China. I don't know where is the installation of this radar. I don't found any information. You are lucky because you know which type of radar in India is used. 99% it is only LDIS company from my city, Pardubice. Then Lockheed Martin, maybe you know this company, US company. It is, I think, one of the biggest one and very well known. This Lockheed, it is really nice, good product. It is high-end product, but of course price will be also high-end, I suppose. It is 3D long-range radar working in L-band. It is transportable. So it is not so huge. Range up to 300 nautical miles, so about 500 kilometers. It must be huge, powerful. And azimuth resolution under 1 degree and elevation also 1 degree. It is impressive parameters for so long range radar. Demonstrated capability to see through the blades. Okay. It sounds very fancy that is no masking under blades, but check these blades. Even with this rotation, if you imagine what is speed of light when your, how to say, signal transferring, it is from 99% free space in this circle. So this masking after wind turbines, it is not huge. Problem is in exact place where is wind turbine. This, if you expect that this rotation speed will be very high, and then radar don't see anything until this wind turbine, now he can see relatively easily. He don't see like 2-3 range resolution cell so well, but after this he can see everything, because imagine this is not solid, it is just 3 blades. And it is this radar, I think that is more military, because it's used of military, of defense and NATO partners. You can't find more information because it is military stuff, so of course I don't know. Then is C-Speed light wave radar. It is low-cost infill radar for ATC application, designed to restore coverage in wind farm sector. It is just designed for wind turbines. It is nice solution, range from 20 to 60 nautical means, depending on configuration. It is 2D radar only. It is compact. Some installation is in North America and UK. This is nice solution. I think that these people also making radar for bird detection, because you know that birds are problem close to airport, because there was multiple failures due to these birds. So they have some experience for detection of this small target and all this stuff. So I think that this is some variation of this. So there you have the whole summary of all things that I already found it. It is not mean, please, that is all of them, all solution. I just tell you I don't found any other solution. So it is about this, about 2, 4, 6, 8, 10, 12 solution, 12 producer that has some information about wind turbine mitigation. Probably will be much more, but I don't know them. Okay, it is lecture 3, and I think that we could make short break. And okay, so I will continue with number 4. No problem. So now I will focus in lecture 4 to general modeling approaches for radar reflection from wind turbines. It will be more about maths and about influence, what we can expect from wind turbines phenomena. This will be like introduction how we like mathematical model of, like our approach of mathematical modeling, and in the next lecture tomorrow we will focus on implementation to real MATLAB model, and in Thursday we will be devoted to design mitigation, like design measurement chain, how we can measure. And on Friday I will show you complete mitigation algorithms. And of course from tomorrow we'll have lecture, tutorial 2, in Thursday tutorial 3, and Friday tutorial 4. So it will be like this continue. Okay, just give me a second. I am thirsty. So These slides give us view about modeling strategies for wind turbine radar reflection. Just really base model is that we have scene, and what is scene? Everything what is in environment, what influence where is position of radar, where is position of wind turbines, and so on and so on and so on. So it is everything in the environment except two things, wind turbines and radar. Because wind turbines is another input for me, and another input for me, last one, is sensor or primary radar system. Our model is modular, so if you want make extension for another type of pulse in a radar system, for another, I don't know, filtration method, anything, you just place function and you could add and adopt it easily. If you want make some better improvement in scene modulation, also you can. So, scene is, how I already say, everything except wind turbine and radar. You could make derivation of this from simple model where is free space plus ground reflection, and we use this approach because we don't consider any digital elevation model except line of sight. Of course, it must be visible or not visible. If it's not visible, I don't care because it not influence me. But I mean this, it is, I didn't consider if between wind turbine and radar it is woods, it is pond, it is lake, something like this. Why? What do you think? Why I didn't consider this? Okay, so we will make a break because it is first slide, so if never mind, I will continue. It is just one slide, so we will take a break and then we'll continue. I think that this lecture 4, I will have it for 1 hour and a half, almost 200, something like this, and will be done. So I little speed up. Lecture 3, it will be shortened, so we are in good way. Okay, thank you.